the confusion. I was kind of didn't know where I am currently. So this is a talk about some preliminary results about existence and non-existence of complex equiangular tight frames. Okay, let's see this. Down. Oh, down. Okay. So what's a complex equiangular tight frame? We fix D. D will be a dimension, and the set of n vectors v1, v2 up to vn in the complex d-dimensional space form an ND equiangular tight frame. If the vectors are of unit length, they are equiangular, that is the inner product or angle between any two distinct vectors is the same constant. We call this constant alpha, and it's called the common angle between the lines. And if there is a third condition, namely the frame operator, if we form by putting the column vectors, these column unit vectors next to each other, satisfies ff star is n over d times I. This means that the rank 1 projections projecting onto the lines spanned by these vectors form a resolution of the identity matrix up to some scaling. Okay, so at this point and at my mental level of understanding, equiangular tight frames for me are just some highly structured, nice, complex equiangular line system. Okay, by the third condition, because of this, we see that we need at least how am I bounding? So we need at least d vectors to have an ETF, and there is a general absolute upper bound for the number of lines, and it's at most the dimension square. The reason for this absolute bound, absolute upper bound, is that if you form the rank 1 projections, the Vi star matrices, those are Hermitian matrices, which are in a sense linearly independent on the space of Hermitian matrices, and there is a dimension that's d square what we get there. Okay, and the problem is to determine for all triplets, for all dimensions d, for all number of lines and all possible common angle, the existence and non-existence of complex equiangular tight frames. Okay, that's what we want to study. Vi inner product Vj is 0. No, Vi inner product Vj is alpha in absolute value.
No, it's not f star f, it is f star, so it's the opposite.
Yeah. It's not the Gram matrix. Yeah, it's not the Gram matrix. Yeah, okay. Good question. Thank you. Okay. And here is a first theorem. This is well known, that if we have n unit vectors with frame operator f forming an equiangular tight frame in a d-dimensional complex Euclidean space, then there is one and only one common angle alpha for which this can happen. Okay, so if you fix two parameters, the dimension and the number of lines, then there is no choice whatsoever for the angle. The angle is implied by these two parameters. Okay, this thing actually is the smallest possible angle for which you can fit this many lines in this particular space with common angle. Okay, and there are some trivial examples. If alpha is 0, you can have just an orthonormal basis in 3-dimensional space. You have 3 vectors. You can have a regular simplex, okay, and then you have a different angle there. You can have even more lines. You can have 6 lines from the icosahedron, and you can have 7 lines from a skew Hadamard matrix, and you can even have 9 lines, but in the complex space at alpha equals 1/2, and this is a PUVM, or what is called complex projective 2 design, I guess. Okay, so these are the known examples, and I still need to fully understand that this frame theory concept, how does it fit into the spherical T-design concept most of the people here interested in. I don't really see the full correspondence between them, but there is a paper by Roy and Scott on Archive. It's a quite lengthy, detailed paper, and he partially discusses what's the connection between equiangular tight frames and T designs. Okay. So Gram matrices and signature matrices. So we want to study these line systems, and we can study them through the other matrix, what we haven't studied yet. Okay. So if F is the frame operator, then we can consider the Gram matrix F star F. So F star F is I plus alpha times Q, where Q is a self-adjoint matrix with 0 diagonal and absolute value 1 entries otherwise. And additionally, it satisfies a quadratic equation. Q square is just a linear combination of I and Q, where mu is implied by all the parameters. Okay? And the proof is very easy that this quadratic equation holds, because if we take this 4 product F star F, F star F, okay, then it's just twice this I plus alpha Q. But in the middle we have an FF star, which by the tight frame condition is n over d times the identity, so I just can plug it out, and this F star F is once again what we have earlier. If you do the maths, then you will get this equation over there. Okay, so if we have an equiangular tight frame, then there is a signature matrix which has precisely 2 eigenvalues. And it turns out that most of the examples what we have are in a strong relationship with very nice combinatorial objects which are well studied. In the beginning I told you something about Hadamard matrices. Godzilla and Ada-chan classified those cases where the signature matrix somehow trivially come from a complex Hadamard matrix, and they showed that if this They showed that if this frame quotient here is between -2 and 2, then this signature matrix is essentially the non-diagonal part of a complex Hadamard matrix. So if you have a certain kind of complex Hadamard matrix, you can construct equiangular tight frames, and the other way around, but of course just within this very, small subclass. And we indeed have examples, because if n is square, then in square orders we can lift the Fourier matrix of order n with a tensor product-like construction, which will be a self-adjoint matrix with constant diagonal, and it will satisfy all these conditions here. Okay, so the point is that Hadamard matrices, complex Hadamard matrices, self-adjoint complex Hadamard matrices, self-adjoint complex Hadamard matrices with constant diagonal are related to a class of equiangular tight frames. Okay, good. Some explicit examples. Just we have identity matrix. This is the simplex, and these are a 1-parameter family of 3 frames, and for generic choice of T, the arising Gram matrices, and hence the ambient tight frames are inequivalent. Okay, so it's an infinite family of essentially different inequivalent solutions. Okay, and in dimension 9 there is another example which comes from a self-adjoint Hadamard matrix. It's once again contains 1 parameter. Okay, these examples testify that this problem is not finite, and it's just not like some enumerative combinatorics or just some easy case-by-case analysis, but there is some analytic structure here. Non-existence results. So in the previous slide I show you some concrete examples. Now there are some concrete non-examples. If the number of lines is at least d plus 2, then n equiangular lines, an n equiangular tight frame in dimension d exists if and only if n equiangular lines in dimension n minus d forming a tight frame exist. Okay, and this duality comes from the Gram matrix. If I have the Gram matrix of one of these 2 objects, then I can negate it, take the negative, then rescale such that the angle will be the correct one, and just add up the identity matrix so that I will end up with a positive definite matrix. Okay, so it's a trivial trivial correspondent to two things. We have this technical condition here that n is at least d plus 2 because in one dimension you have as many equiangular lines as you just want, because you can just take the same vector over and over again, and the implied angle between them will be just 1. Okay, so it's not an interesting example. Other than that, you have this result here. Now, the corollary, if once again this technical condition holds and we have an ND equiangular tight frame, then of course n is at most d square. This is the absolute bound, but by this duality result, n cannot be larger than m minus d square. Okay, and if you do the math, it turns out that the Neumann complementation tells you that in an ETF the number of lines is bigger than just d. Okay, d is not enough, but you need d plus, I don't know, root d or something vectors, otherwise you cannot have an ETF. Okay, so in concrete example, you want to ask, is there a 5-3 equiangular tight frame? So 5 is below 9, so in the first round it survives the necessary condition of the absolute bound. But if you pass on by normal complement to the 5-2 case, then you see that in 2 dimension you cannot have 5 vectors, because in 2 dimension the absolute bound is 4. Okay, so this case is that. That's how people use the Neumann complement. And this is the one and only non-trivial, non-existent result in this area. Okay. Joel Trop, Dion, and 2 other guys around 10 years ago published a paper where they used this alternating projection method. It's a numerical search, and they compiled a large table where they confirmed the existence of all known trivial existing examples, and didn't find anything new. And this is the state of the art of this problem. So this is a table from dimension 2 to 6 with number of vectors from 3 up to 36. You cannot have more than 36 in dimension 6. And well, we have some sporadic examples only. Okay, we can't have too few lines in an ETF. We can't have too many lines in an ETF. And between the two things, the Neumann complementation, which provides a gap here between the existing examples and the non-existent examples. Okay, so these cases doesn't exist, and today's contribution is a confirmation of 2 more examples, or the non-existence of 2 more examples here, and these are the first of their kind. Okay, so only the Neumann complementation what was known. Well, we add 2 non-existent cases to this zoo. Okay, so main results of today's talk. First, there does not exist 8-3 complex equiangular tight frames, and hence by Neumann complementation there doesn't exist 8-5 complex equiangular tight frames either. Okay, this is one result. The second result is that all 9-3 complex ETFs are known and were known previously, because I obtained complete characterizations of all 9x9 self-adjoint complex Hadamard matrices. Okay, since I know all the Hadamard matrices, I know all the corresponding equiangular tight frames. And well, in the second case, I only confirmed that there are no new examples. So I was hoping to find something new, but the result is that there is nothing beyond what we already known. And the proof is by computer calculations. I will see what I can say about this. Okay, so the main idea to get these results is to understand the structure of a subconfiguration of a hypothetical or an existing equiangular tight frame, and these results what I got could be achieved by investigating 6 equiangular lines, or in other words, a 6x6 subgram matrix or a 6x6 partial signature matrix, and the following 2 observations what I made, which lead to the results I announced previously. So in the non-existence case, if I take any 6 lines in the 3-dimensional complex space where the common angle between the lines is what is required to have an 8-3 tight frame. Okay, so remember that the dimension and the number of lines forces you to choose an angle. So any such configuration cannot be extended with further lines. Okay, so at this particular angle, root 5 over 21, you can have at most 6 lines. And the second result, what concerns the 9-3 frames, is that such a frame, the gram matrix or the signature matrix of such a frame is either formed by 6 roots of unity. Okay, so there is some scaling that the diagonal is 1 and the other ones are 1/2, but in essence 6 roots of unity. Or if not, if there is an entry which is not a 6 root of unity, then actually there are 3 which are form of vanishing sum of order 3. That is, if you have 1 non-cubic element, then you have 3 which sum up to 0. Okay? So these structural results of relatively small subconfiguration lead to existence and non-existence. Okay. Okay, so these calculations and computer calculations were obtained by means of Groebner bases. Just very briefly, a couple of things about this. So if we have a system of polynomial equations, then there is an algorithm which decides whether these polynomials have a common root or not. Okay, so you just put these polynomials into the computer, hit enter, pray, wait for forever, and then it can give you a definite answer if you don't run out of memory and if you are patient enough. Okay? Now, even more, if the polynomial system has just finitely many solutions only, then there are efficient ways to actually extract these solutions by obtaining a so-called triangular form, which is if you have m variables, the triangular form is just m polynomials, the ith one depending only on the first I variables. Okay, and the common roots of these are precisely the solutions of the original system. So you just solve first polynomial and figure out what the values of x1 can be, then just plug it into the second one, and then it's just a polynomial in x2, so you can solve it for x2, and then you plug in for the next one, you plug in for the next one, so you can recover all the solutions, so you can get a complete understanding of the system. However, if there are infinitely many solutions, then there are some theoretical results, but nothing really works in practice. So that's really inconvenient to study an infinite solution of a polynomial system. Okay, so the number of terms and the number of degrees can very quickly blow up, and then there is nothing you can do. So the best thing, and the message here, is that almost the only way to use this approach and use these Groebner basis techniques is to ask the computer to prove me that there are no solutions whatsoever. Okay, because no solutions means that eventually these larger and larger polynomials will just die out, and in the end you will end up with a 1 in the ideal. Okay, so it's much better to force the computer to prove your non-existence than to ask what are the solutions. The solutions are many. There are huge polynomials which are inconvenient to work with. Okay, so in the 8-6 case, when there is non-existence, the following idea was used. So the result is what I announced already, that 6 oh no, this is another result. So in fact there do exist 6 equiangular lines with this common angle what we want. Okay, it could happen that there are no such configuration and we already won. Bad news is we have such a configuration, but none of these can be extended to 8 lines, and then the question is why. So assume that there is indeed an 8x8 gram matrix which you can get by extending these 6 lines what you have. Okay, this gram matrix, take 3 rows from this gram matrix. The left part is the known part given by these 6 lines you have, and the right part with these u's are the unknown part. Okay, now since G is a projection, or essentially a projection, we know that G square is n over d times G. This is just I guess the tight frame condition. So the left hand side we have the inner product between the ith and jth row. This is the ij entry, and the right hand side says that this depends only the ij entry of G. Okay, and then by linearity this inner product can be split to the known part and the unknown part. Okay, so I do the same equation for the first, second, the second, third, and the third first rows, okay, for 3 indices, I get 3 equations here. And if I average out, if I multiply these 3 things together, it turned out it just so happens to be that the product of the right hand side is identically real. It's just an algebraic identity, which no matter what you plug in here for you, will be just happens to be a real number. Okay? The left hand side here, however, doesn't identically real. So this condition here gives you new information how this known matrix should look like. The entries in this known matrix should look like that after this averaging out thing, whatever you have is a real number. So this is a new information, okay? And this condition here can kill some hypothetical solutions, because this product of these 3 quantities is just not real. Then they cannot be extended. Okay, and well, this is unfortunately, however nicely these look, these are not my ideas, but they were developed by Uffe Hagerup, who is a operator theorist. When he was fully classifying the 5x5 complex Hadamard matrices, he came up with an identity very similar to this. So we have 6 unit numbers. We have 6 unit numbers, and from these 6 unit numbers we form this triple product here. And it just so happens to be that this is identically a real number. This is what I showed you in the previous slide. But what this real number is, it's just not some random real number. It's not just an arbitrary real number. This real number is actually can be expressed in terms of the factors here in this way. Okay? So this is just an algebraic identity, and this setting here with this triple product can be applied to this matrix and to this setting here, resulting in this, well, kind of technical statement here. Okay, so this theorem says that if you have a n-2 times n-2 partial gram matrix, and you form the partial sums, which was denoted by A in the previous slide, then you consider the triple product. The triple product is a real number, in particular this quantity here. Okay, and this identity features only the n-2 times the entries of the m-2 times m-time leading principal submatrix of any hypothetical gram matrix G. Okay. Okay, so now we need to implement all these ideas to a computer system. So we seek for a 6x6 subgram matrix H with normalized entries. Main diagonal is 1. The first row and column, once again by normalization, just the angle, what we want. And all entries have, all other entries are just alpha times xij, where xij are unimodular. This is important because then complex conjugation is just 1 over xij, so we can form polynomials from these quantities. And what are our conditions? Well, our conditions is that the angle is whatever the tight frame condition implies. This is described by this quadratic equation. Then we are in the 3-dimensional complex space, so the rank of the gram matrix, and in particular the rank of the subgram matrix, is at most 3. Hence all 4x4 minors must vanish. These are once again polynomial conditions. And then h square minus n over d times h has rank at most 3, because we threw away 2 rows and 2 columns from the matrix. So once again, it's a minor condition. And these alone doesn't powerful enough to conclude non-existence, but we have this Hagerup type identity I introduced in the previous slide. If we apply this, all triplets of rows, this is a new extra condition. And the last condition is that none of the xij's is 0, and you can guarantee this by multiplying them all together with an extra new variable u, and say that, okay, I want this product to be -1. Then none of these quantities can be 0, okay, if the total product is -1. Okay, this is just a technicality. You ask the computer whether there is a common solution or not, and the computer will tell you there are no common solution. Okay, so we could succeed here because we could use the unimodularity constraint in how to say effectively. Okay, so these are one of the results, and I guess I can tell you about the other one. So this here is a gram matrix of a one-parameter family of complex equiangular tight frames in 3 dimension by 9 vectors. Okay, and if you look at this matrix, you immediately realize that this is essentially a Hadamard matrix. So, and indeed, if you just rescale and get rid of the identity, you can get a Hadamard matrix H9. And by the theorem in the beginning by Godzilla and Chan, fully understanding self-adjoint complex Hadamard matrices with constant diagonal amounts to fully understanding these kind of equiangular tight frames. Okay, the question is that is there a 2-dimensional family, or is there some isolated solutions not belonging to this particular family? Okay, these were very well known by people, but are there any further examples? And okay, 3 minutes. Yeah, I see. Okay. There will be no questions. So, okay. So here are some interesting tools. The defect of a complex Hadamard matrix. So assume that you have a complex Hadamard matrix H. Okay, and you ask that how many free parameters can you put into this matrix. Okay, this is very relevant to the previous slide because we see a 1-parameter family there, and I ask, can we put 2 there? So what you do is to consider a phasing matrix K with unit entries e to the I times xij, and you ask that for what choice of this matrix K will be the Hadamard product of your original Hadamard matrix and this phasing matrix be a complex Hadamard matrix up to first order. Okay, so you linearize these quantities here by Taylor expansion, and you want to have that this matrix is a Hadamard matrix after linearization. It's a kind of cheating, but it gives you some kind of information. Now this describing the orthogonality up to this error is a system of linear equations. You can ask, what's the solution space of this system of linear equations? The dimension of the solution space of this thing here will give you an upper bound on the number of free parameters you can introduce into the matrix. Okay? Now the same concept can be applied to self-adjoint Hadamard matrices. The point is that if you just pick a typical example from that 1-parameter family, its defect will be 2. So analysis tells you that there could be a 2-dimensional family. If you pick a very special particular matrix, this defect is 4. It tells you that around the small neighborhood, that particular matrix, there could be a 4-dimensional family. So this is a kind of an evidence supporting that there could be a larger family than just what we have. Unfortunately, despite these high hopes, there are no such examples. And why? Because we can once again set up some polynomial equations in a very similar manner than previously, and there are many solutions. There is a 1-dimensional family of solutions. It's impossible to calculate those. So we ask the computer, are there anything beyond that? Okay, and how do we do this? Well, we observe from the previous slide here that either all these entries here within the matrix are 6 roots of unity, or if not, if they are, let's say, ugly entries, then they are not alone in that row and column, but there are some companion entries which are just rotated by this ugly entry by whatever, the cubic root of unity or its square. Okay? So I ask the computer, are there solutions where I have some non-cubic entry and non-6 root of unity entry, and there are other 6 root of unity entry, but they are not rotated of each other, and this condition is this one here. Okay, so I just put this here and I hit enter, I pray, and the solution is, or answer is, no, there are no such solutions. So what do we conclude from this? We conclude from this that tight frame either from 6 roots of unity, or if not, then we indeed the ugly entries are just rotated from each other, and then just a standard and automatic analysis shows you that there are no further examples than this matrix here. Okay, I spoke too much. Thank you very much for your patience and attention.